question. Can I erase this? And this is interesting. Let's consider a magnetic field that let me make it straight down. Okay? So let's say everywhere, or would you prefer it to be up? I don't know. Let me go with what you guys think.
Down is fine.
Down is fine? Okay. So what if there is a region of space where there is a magnetic field pointing down? And it's uniform, to make it simple. So this is a uniform, I'll say external magnetic field of magnitude B. Okay? So it's just there. Huh? Something is generating this magnetic field. So now what happens if I take this loop, and suppose I put this loop like this, or like that, it doesn't matter. In fact, let's make it, how about I make it a rectangle? Okay, so I take a loop, and I put it right, and I'm gonna use a different color so it stands out. So what if I take, let's call this A in length. Let's call this B in length. So this is just a rectangular loop. And suppose that this rectangular loop has a current in it. So in which direction would you like that current to be? Around that loop, clockwise or counterclockwise?
Clockwise.
Clockwise, okay. So let's make it clockwise. So the current on this segment will be to the right, yes. On this segment, the current will be down. On this segment here, the current will be to the left, and over here, the current will be up the board. For you, up the page. So it's there. How about this current is constant? Okay, so magnetic field pointing down, everywhere in this room. I take a rectangular loop with current in it, and I place it in this magnetic field. So what will this external uniform magnetic field do to a rectangular loop that has current I in it in the clockwise direction? First of all, let's consider this rectangular loop with 4 segments, 1, 2, 3, and 4. Let me just give them names. So let's say this is number 1, this is segment number 2, this is segment number 3, and this is segment number 4. Okay. Which segments will experience zero magnetic force?
2 and 4.
2 and 4, how do you know?
They're parallel with the magnetic field.
Exactly, agree? Segments 2 and 4 will experience zero magnetic force because, I guess I erased the expression, right? The force would be Li cross B, right? So if the current is in the same or opposite direction to the magnetic field, the cross product is going to be zero and there's not going to be a force. So segment number 2 has a current pointing down in the same direction as the magnetic field. The force on it is going to be zero. Segment number 4 has a current going up the board, which is opposite to the magnetic field, which is down the board. So the force on it is going to be zero. What about segment number 1? What is the force on segment number 1? So let's calculate that. Is it zero or no? No, so let's calculate the force on segment number 1. So what is the force on segment number 1? Just segment number 1. It will be what? It will be the length of segment number 1 times the current in segment number 1 crossed with the magnetic field that it's sitting in, right? So what is the length of segment number 1? What did I give that length? B, right? And what is the current I1 or the current in segment number 1? It's I to the right, correct? Cross with the magnetic field at the location of segment number 1, which is B. And we made it down the page, right? Everywhere we made the magnetic field B down the page, right? So what is this force on segment number 1 going to be? Well, it will be B times I times big V B. And then the force is going to be in the direction of this cross product of to the right cross with down. So what is the direction of to the right cross down?
Into the page.
Agree? Into the page? Is that good?
Mm-hmm.
Okay, so this would be into, in this case, the board. And for you, the page. All right. In other words, this segment is going to experience a force into the page. Like if I put it like this, at the top, it will experience a force into the page. Now, what about the force on segment number 3? Is it going to be 0 or no? No, right? So what is the force on segment number 3? So this was one of them. Let me calculate the force on segment number 3. It would be what? It would be the length of segment number 3, right? I said 3, but I wrote 2. It would be the length of segment number 3, right? Times the current in segment number 3, which is I to the left. Well, I'll write it out. I'll write down the formula and then plug in the cross into the external magnetic field. So the force on segment number 3 will be the length of segment number 3. What is the length of segment number 3?
B.
B. What is the current in segment number 3? I to the left, right? Cross. And what is the magnetic field that segment number 3 is sitting in?
B down.
B down. Right? So this will be B, I, capital B. And in what direction is this? How much is to the left cross down?
Out of the board.
Which one? Out of the board? Interesting. Notice, do they have the same magnitude? Yes, right? So do they cancel each other out? The force on this one, suppose this turns out to be 5 newtons. And the segment at the top is going to be 5 newtons this way. And for the segment at the bottom, 5 newtons this way is going to be 5 newtons out. So the forces cancel each other out, right? So the net force is going to be 0. So, the sum of the forces is equal to the mass times the acceleration of the center of mass, right? But this one is going to be 0. So the acceleration of the center of mass is going to be 0. So that means that the velocity of the center of mass will be constant. But since it was 0 to start with, it'll just stay at 0. In other words, this loop is not going to go anywhere. But there's a but. What happens if I grab that end and I push it that way, and I pull this one out this way? It'll spin. So if I grab this, the center of mass will stay put. This one is like I grab this and I'm gonna pull it into the board, and this one I'm gonna pull it out of the board. So I'm gonna go like this. So it's gonna spin. In other words, this magnetic field is exerting a torque on this loop.
So is it just like in a perfect balance, and that's why?
No, it's gonna spin. If I hold it, it will stay there. But if I let go, this thing is gonna go like, it's gonna spin.
Okay.
So we want to know which way is it gonna spin. Where does it want to go to? So is it gonna stop spinning if I leave it alone? So there are a couple of ways. So let's calculate the torque exerted by this magnetic field on this loop. And we can do it in a couple of ways. There's a quick way. And if you remember a result from Physics 185, in Physics 185 there's a Hoover problem that I assigned, which in chapter 10 of the textbook, which deals with the torque of a couple. So it's torque of a couple. In physics, what is a couple? So a couple is when there's a force, let's say this way, of some magnitude, and there's another force that has the same magnitude pointing in the opposite direction, but not along the same line of action. So something like this. Right. The line of action of the first force is this, and the line of action of this one is like that. So a couple is comprised of two forces that have the same magnitude and opposite directions. But gee, you could have like when I stand on the ground, right? That's the ground, this is me here, right? And then there's the normal force and there's the weight. And if I stay put, my acceleration is 0. So this has the same magnitude as that. And they point in opposite directions, but they share the same line of action. So it's not a couple. So a couple would be, they have, there's got to be a distance between one line of action and the other line of action. It's called D. And there's a Hoover problem where if you calculate the torque of a couple, see, when you calculate the torque of a force, it's R cross F about point P, and this, so it matters about what point you take the torque about. But when you have a couple, the torque exerted by a couple is independent of where you take the torque about. It's always the same value, and same magnitude, same direction. And the easy result is that, well, this force is like that, this force is like this, so the torque is going to be, clockwise, and the magnitude of the torque is just the magnitude of either force, because they're the same, multiplied by D. So if you want to know what is the torque quickly, what is the torque that this magnetic field exerts on this loop, right? Then you say the force on this is 0, the force on that is 0, the force on segment number 1, right, is I, B, or BI, capital B, and it's into the board, right? While the force on segment number 3 is the same magnitude, IB, but it's out. And they don't share the same line of action. This one is into at the top, this one is out at the bottom. They don't share the same line of action. Those two forces have the same magnitude, and they're like this. They don't share the same line of action. So they're a couple. And very quickly, what is the torque of that couple? Well, if this one pushes into the board at the top and this one out, the thing is going to spin this way, right? So the torque as a vector, you could say the torque as a vector is to the left, and the magnitude is just this force multiplied by this separation, which is A. So the torque is going to be as a vector, very quickly, it will be just the force times A, and it will be, to the left. Because this top is going to spin into, this one is going to spin out. If I use my right hand, the torque is to the left. So this is just going to be very easily, very quickly, if you remember that other result, of course, the magnitude of the force is I. And then if you multiply this A by this B, it will be A times B, and then the big B to the left. That'll be the torque. If you remember what the torque of a couple is. If you don't remember that, you can do the cross product. So let's do it like that. And then I'm going to teach you a shortcut for calculating another, an expression for calculating the torque of a force, right? So essentially, I have, it doesn't matter what point you take torques about, right? So, it doesn't matter. So we have a force at the top. That's F equals I or B, I, capital B, and this is into the force at the bottom, which is B, I, capital B, but it is out, right? And the distance between these two is A. And suppose I take torques about this point. It won't matter what point I take torques about, so I'm just going to take the torque about point P. So this would be R cross F. This R is a vector. When you take the torque of a force, if I have a force like this, F, and I want to take the torque of that force F about this point P, then the torque is given by this expression where this is the line of action of the force, and then R is a vector that begins at point P, and the terminus of it ends anywhere on the line of action. So R could be this, it's got an end over there, or R could be this, R could be this, R could be this. It's going to start at the point that you're taking torques about, and it's going to end anywhere on the line of action. Right? So I want the torque of these two forces about, let's say, point P. So what would be the torque of this force about point P? This force has a line of action. The force at the bottom, this one here, has a line of action like that. And what is the distance between point P and that line of action? 0. So there's no torque of that force about this line of action, about this point. So that would be 0. So the only one that will contribute to the torque is going to be this one. Actually, this one was out, but the line of action was in and out, right? So the only one that matters is this one. So for that one, the line of action is like that, the point is like this. So I draw R from here to there. I'm gonna use a different color for that. So it's gonna end, I'll just pick this R. The magnitude is A pointing up, that's point P. So this will be, R would be, the magnitude is A, and the direction is up. Cross with the force, which is this one. B, I, B, into the board. And that we should be able to do relatively quickly. So I have A, B, I, B, so I'm gonna write I, A, B like this, and then B. Notice that that's the same as this. And then I have up, cross, into. So how much is up, cross, into? So the magnitude is I, A, B, times B, which is up, cross, into. To the left. And that's the same as this, right? And if there is a torque, which in this problem there is a torque, as a vector, the torque vector points to the left. And if there is a torque, there is a, rotational effect. How would the thing rotate? Put your thumb of your right hand in the direction of the torque vector, and then the thing is going to rotate in the sense indicated by your four fingers. At the top is going to go into the board, the bottom of the coil is going to go out of the board. So the coil is going to rotate like this. The top going into, the bottom coming out of the board. Now, do you notice that we have I is the current in the loop, B is the magnetic field that the loop is sitting in, right? The external magnetic field. And what does this represent? A times B.
The area?
The area of the loop. It's a rectangle, right? If you multiply A by B, is the area of the loop, right? So there's another expression that we can use to figure out the torque that the magnetic field will exert on the loop. And it's like this one. So we have to introduce what this quantity mu represents. This one, this quantity mu, represents the current in the loop and also the area of the loop. It's a simple definition, you'll see. It's a quantity that has a difficult name that makes it sound difficult, but it really isn't difficult. What's difficult about it is the name, but the quantity itself is not difficult. And also, when I said a little while ago that this is really cute, is because if you think about it, right? What is it that we have over here? We have a magnetic field that what we said was, let's say it's everywhere in this room, and let's say we said the magnetic field is pointing downwards, right? And if I have a coil with current in it, and I place it in this magnetic field region, what is the magnetic field gonna do to this coil?
It'll apply a torque on it?
And it'll make it spin. Notice we're getting kinetic energy. And that energy must be coming at the expense of some energy somewhere, some potential energy somewhere. So when this coil has current in it, and it is in the presence of a magnetic field, there is energy stored in the system. It's called magnetic potential energy. And when the coil then spins, there's kinetic energy showing up. In this case, it's actually rotational kinetic energy, 1/2 times the moment of inertia times omega squared. But that energy is coming at the expense of the magnetic energy stored in the system, comprised of the coil with current in it and the magnetic field. And the other thing that's cute about it is that, well, you can wonder, well, wow, it's now spinning, and now it's got kinetic energy, which is coming from the it's gotta be coming from somewhere, right? So some stored magnetic energy has to then be decreasing, and that decrease in magnetic energy is getting converted, transformed to kinetic energy. But the other nice thing about it is that, you can use electromagnetic phenomena, magnetic field, magnetic current, electric. You can use electromagnetic phenomena to get something spinning. And that's the basic operation of a motor. In a motor, right, any motor, right, that's made to spin, where is that, rotational kinetic energy coming from? It is coming from electromagnetic energy. And how does that come about? Well, there's got to be a current in some loop with forces in opposite directions exerted by there's got to be a magnetic field in there, right, that will then exert forces on the various segments of the loop, making it spin, exerting a torque on it, making it spin. Right? So, you all of a sudden you got something, something that now can have rotational kinetic energy. That rotational kinetic energy, may be used to make the thing move, right? Mechanical energy out of electromagnetic energy.
We can do the opposite thing, right? We can spin the loop.
Exactly. And in chapter 29, the next chapter, what we are going to do is we can have the loop, right, with no current in it. In fact, in the first case, what we're considering is, I said, suppose there's a current in it. So maybe there's a little battery over here that drives a current, right? But suppose we have a ring like this. A ring with no battery attached to it, no function generator attached to it that then runs a current, creates a current, establishes a current in the ring. Just a ring, a metal, right? And if I put this metal in the presence of a magnetic field, and I change the amount of magnetic field that goes into and out of this loop, I don't know, maybe this is a bar magnet, and I go in, out, in, out, in, out, in, out. As I do that, I am changing the amount of magnetic field, right, that goes through this thing, and that makes a current in the ring. So in that case, I use mechanical energy to create an electric current. That's a generator. That's how you generate the electricity, right? Something is, or I can, there are various ways that I can change the amount of magnetic field going through the ring. I can move the magnet closer, farther away, or I can leave the magnet alone, for example, because maybe the magnet is too heavy to move in, out, and I can take the coil and I just spin it. And as I spin the coil, I'm putting in kinetic energy, then an electric current shows up in the coil. And that's how you make electricity. So the electrical power plants, all electrical power plants, right? There's water somewhere, and then, well, not all of them. Well, okay, I'll tell you where the differences are. But, in the conventional electrical power plant, there's water somewhere in a pool, and then you start a fire, burn coal, whatever, you start a fire, right? The idea is to raise the temperature of the water so that the water boils. And when the water boils, it turns into steam. And then you take that steam that came from the liquid water, now it's water or steam, right, in the gas phase, and you take that and you pass it some conduits, some tubes, and then in the way of those tubes, you put like a fan with blades. And as that steam blows past the fan, the blades of the fan, the blades turn. And as the blades turn, a coil in the presence of a huge magnet, as the blades turn, the coil turns. And that makes electricity. I said all electrical power plants have that. Well, in the case of a nuclear power plant, the only difference between a nuclear power plant and the plant that I just described is where they get the energy to boil the water. And they just have some nuclei of uranium-235 undergo some nuclear fission reactions, which produces energy, and then that energy resulting from the nuclear fission reactions, that energy is just used to boil the water. But the rest is the same. You make steam, the steam goes past the blades of a turbine, which then with the steam makes the blades turn, and as the shaft of that turbine is connected to the coil and it spins the coil in the presence of a magnet, there you go, you make electricity. But at the Hoover Dam, for example, outside Las Vegas, I don't know if you've ever been there, but you should all visit, once, or at least once. Over there, it's only like 15 miles southeast of Las Vegas, 15, 20 miles, not farther away than that. It's a place that's worth visiting, and you can take the tour. Over there, what happens is there's the river, and then there's a big drop in the level of the river. And as the water falls, it hits the blades of a turbine, right? So you're not boiling water to create steam and have pressure to then spin the blades of the turbine. Over there, you don't boil anything. It's just the water is coming down, and you use the water coming down. It hits the blades, and it makes the blades turn. What they do over there, though, is they don't spin the coil. They actually spin the coil. It stays put, and what they do is the blades of the turbines spin the magnet. Well, what matters is the relative motion between them. So they spin the magnet instead, and the coil stays put, and then that's how electricity is generated. So there you use, the gravitational potential energy of the water as it comes down, right? It turns into kinetic energy, which hits the blades of a turbine, which then makes the turbine blades turn, and that's attached to the magnet that's moved in the presence of a coil. In the other ones, the other more conventional electrical power plant and the nuclear power plant, you have the water, which is then brought to a boiling point. The water boils, turns into steam at high pressure, and then that steam is passed down these blades, which then turns the blades, right? What about Palm Springs? Palm Springs is pretty windy. So in that case, you just put the blades of a fan up there, the wind blows and the blades turn. And as the blades turn, a loop down somewhere at the bottom at the base of that unit, a loop spins in the presence of a magnet, and that creates electricity, and that can be used to power 100,000 homes or something like that. So in that case, you're not boiling water, right? And you're not having nuclei of uranium-235 split. You're not using nuclear energy to boil the water. So over there, you don't even use water, right? It's just the wind. The wind is blowing. You might as well try to harness that energy in the wind to make a blade spin, and then as the blade spins, right? They turn a coil in the presence of a magnet, and then make electricity. So those are opposite processes to what we're talking about here. In this case, the current is there, right? We're not asking right now what's generating the current, but suppose there's a current in this coil, and this coil happens to be in a magnetic field. Magnetic field will make it spin. But the reverse, so that's right. So that's what happens in a motor. In the reverse process, where you move the thing to make electricity, is called a generator. So a motor is really, operates in the reverse of a generator. But let me say something about this quantity, okay? A complicated name for something that's not difficult. So if there's a loop, so for a loop, and the loop doesn't have to be a rectangular. In fact, I'm gonna draw 3 loops. I'm gonna draw a rectangle, I'm gonna draw a circle, and I'm gonna draw a triangle, you know, for fun. The loop can be triangular. So, this is oftentimes called a current loop. That means a loop with current in it, right? Not like, you know, a loop in the present. So what if we have a loop like this? Okay. Number 1, a rectangle. Let's say this is 2 meters and this is 3 meters long, right? So what is the area of this loop? Let's take care of that because then that'll make it a lot simpler, I think. What is the area of that loop?
6 meters squared.
It will be 6 meters squared, correct? So for this rectangle, the area is, well, 3 meters multiplied by 2 meters, which is going to make it 6 meters squared. But now we talk about an area vector. So what is the definition of an area vector? Actually, we wrote an area vector for Gauss's law, right? What did we say? The magnitude of it is the magnitude of the Gaussian surface, but what did we say about the direction? Perpendicular to the surface. In that case, the surface was closer, it was going outwards. So this loop is at a close, you know, is at a closed surface. So the area vector could be either out or into the board. So the area vector is just a vector whose magnitude is the area of the thing, you know, 6 meters squared, which is 3 meters times 2 meters, but the direction is perpendicular to the plane of the loop. So in this case, it could be either into or out of the board. Right? Now, what I'll do is I'm gonna put a current in here. Now, which way would you like? I'll let you choose to now. What direction would you like the current to be, clockwise or counterclockwise? Counterclockwise. Okay, so let's make, suppose this loop has a current in it. Let's make it, I'm gonna make it 4 amps. So, now that this loop, see, if the loop doesn't have a current in it, then the area vector will be 6 meters squared and it could be into or out of the board. It's gotta be perpendicular to the plane of the loop. But now that I've given you know, that I have established a current in this loop, the way that I select whether it's into or out of the board for the area vector is I use a right-hand rule. I curl my fingers in the direction of the current, and the thumb points out of the board, so I'm gonna say that this is out of the board. That's the area vector for that. I'll do number 2. What if we have a circular current loop? So, a circular current loop. And suppose the radius of this is, I'm gonna pick a weird number. How about I make it 5 divided by the square root of pi meters. So what will be the area vector of this? Well, what is the area of a circle? Pi r squared, correct? So it will be pi times, what is that radius? It is 5 times the square root of pi, right? Squared. Oh, can you see now why I selected that weird radius? So the area is what?
25 meters squared.
25 meters squared, exactly. Now, which way is it going to be? Well, it's gotta be perpendicular to the plane of the loop, right? So it's either going to be out of the board or into the board. Well, how about this time I selected counterclockwise and I make the current 2 amps?
Counterclockwise again?
Oh, okay. Again, I guess. So if the current is counterclockwise, which way would the area vector point? Into or out of the board?
Up.
Which way?
Out of the board.
Out of the board. And I can do another one, a triangle. I can give it a base and a height, and let's not waste time with that. Is that okay with you? Now, so these are just current in a loop, right? This is a circular loop, and we know what the area of a circle is, pi r squared. This is a rectangular, it could be a square, right? But there's current in it. And so we define the area vector like this. The area of vector has a magnitude equal to the area of the rectangle or the area of the circle, but the direction is perpendicular to the plane, right, of the loop, which would be either in or out in this picture, but we just use the direction of the current that's given to select the direction of that. If this had been clockwise, then it would have been into the board, the area vector. Now here's when we define that quantity that has a weird name. So you define this quantity, mu, which is simply the current, just the magnitude of the current, multiplied by the area vector. And think of this as a scalar times a vector gives you a vector. And the current, we're never going to say it's negative 3 amps, or, so this vector, mu, always points in the direction of this vector. So what would be mu for this loop? It would be I times A, right? Which would be the current is 4 and A is 6 meters squared out. So this is going to be 24, and the units would be amps meters squared, right? And the direction is out of the board. I mean, isn't that a simple quantity to calculate? What would it be for the case of this circle? Here, mu would be I times the area vector. So the I made it over here 2 amps. And what is the area vector? We made it 25. Pointing out of the board. So this is going to be 50. The units will be the units of current, which is amps, times the unit of area, which is meter squared. And as the direction is out of the board. Now, remember the rectangle problem that we did with the magnetic field pointing downwards? What was the area vector? What was the area vector for that? It was AB, that's the magnitude, right? AB. And I don't remember, which way was the current? Was it clockwise or counterclockwise? Clockwise, so the current was this way, so the area vector has to be into the board, right? Yes? We had a loop like this. I think I made this A and I made this B, and I think we had the current like, no. I don't remember. Which way was the current?
It was right.
Clockwise or
Yeah.
counterclockwise?
Clockwise.
It was clockwise like that, right? Well, if the current is clockwise, the area vector is into the board, and the magnitude is A times B. And what is mu, therefore? It would be the current I multiplied by that area vector, which would be the current I times AB. But as a vector, it's in the same direction as the area vector, which is into the board. Yes? Now, the torque that the magnetic field exerts on the loop with current in it is given by mu cross B. The torque is just that quantity cross B. In fact, you can write it like this if you like, because mu is the current times the area vector, and then you cross that with the magnetic field, if you want to do it like that. Or mu, calculate mu like this, and then cross that with B. In the problem that we had, the magnetic field was down, right? And the problem that we had, the magnetic field was down. And we just said that the area vector is into the board, right? The mu is into the board. So what is the cross product of into with down? Into with down. So it would be, the direction would be to the left. So the torque would be, for the problem that we did, I, A, B, and then times the magnetic field, right? And to the left. And that's the same as this, right? So that's another way of doing the problem. So this quantity that has this, which is simple, what's difficult about it is the name. It's called a magnetic dipole moment. Right? 3 words to mean one thing. Magnetic dipole moment. It's just like a magnetic dipole moment, and then it sounds difficult. Truly, right? It's like, what? Magnetic dipole moment. But they just say your name was magnetic dipole moment. It'd be nice, you know, next time you meet someone, what's your name? Magnetic dipole moment. I'm gonna do that next time. Yeah. Magnetic dipole moment. So it's just a difficult name for something that, by the way, those of you in chemistry, right? Here is the proton. If you consider the hydrogen atom, right? There's the proton, right? And here's the electron, and the electron is negatively charged. And what does the electron do? Well, it goes around the proton, right? That electron going around the proton, that makes up a current loop. I mean, the current would be like the charge per unit time. Well, the charge that flows in one trip is the charge of the electron, and the time is the period. And the period is the time to go around one, so that would be the circumference, 2 pi r divided by the speed. So that would be E divided by 2 pi r. And if you multiply that by the area of this circular loop, you get mu, which is I times A, which would be that quantity times pi r squared. And then this pi is cancelled, and you get EVR over 2, that's it, right? Well, that's the magnetic dipole moment of the electron due to its orbital motion around the nucleus of an atom. And when you subject, remember we were talking about iron and some materials that you put them in a strong magnetic field, and I said that somehow the atoms align? Well, what happens is that, how much time do we have?
We're about 10 over.
We're done.
Yeah.
Okay. Keep going. So, I'll tell you this and then we can elaborate on it. Remember the problem that I did with the magnetic field going this way? Right? External loop like that? Which way is the area vector of this loop pointing?
Into the board?
Into. So which way is mu? Mu pointing
Into the board?
into the board. Now, so mu is pointing this way, right? So here's the loop with the magnetic dipole moment pointing this way, into the board. Now, which way is the magnetic field pointing? Down, right? So what I'm going to talk about next time is this. When you have a system like this, like a loop with current in it, in an electromagnetic field, remember that I said that there is a potential energy? The potential energy is this. Now it's magnetic, and it's minus mu dotted with B. What do you think is the orientation of this mu that minimizes the energy? If mu is parallel to B, then this is going to be positive, and this is just going to be minus mu B. If mu is perpendicular, the dot product, right, so dot product cosine of 90, that's going to be 0. But what happens if mu is in the opposite direction to the magnetic field? Then that product is going to be negative times this negative is going to be plus mu p. Which of those three energies is the lowest energy?
Negative.
This one. When mu is parallel to this, right? So it's like the magnetic field is pointing down, 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 down. You got the loop like this with current in it, and we said that mu is this way, right? Well, which way do you think this magnetic dipole moment vector wants to point? To minimize the energy. It wants to go down. Well, not go down, point down. So therefore, it's like it says, well, I can go like this, but or I can just go like this. And that's what it does. That's very quickly you can figure out how the thing is going to spin. Right? So what happens is that when I started the problem like that, there was potential energy, and the system says, okay, now you left me alone, I want to minimize that. So I'm going to spin to minimize the potential energy. Just like when I let go of this marker, right, there's potential energy of interaction between the marker and the earth, mgh. It's like the marker. As soon as I leave it alone, it says, oh, I got to minimize my energy. By going down, it decreases h, mgh gets smaller, so it goes down. Now, the marker, of course, when I let go of it, it could decide to go up and then down. But it's not going to do that. It'll just go straight down. Just like this. It could decide to go up, oh my goodness, that's increasing the potential energy, and then go down. But no, the easiest thing to do is to just go like that. And that's what happens when I said, suppose the cops come over here and they say, everybody in the Lewis building face towards the Lewis parking lot, right? And we all go that way. So essentially what happens in the piece of iron, and when you subject it to a strong magnetic field, you have all of these atoms in there with electrons going around, and they form tiny current loops called magnetic dipoles, right? And then when they are subjected to this external magnetic field, it's like they want to line up. They want to align, right, with the external magnetic field. And then you remove the external magnetic field, and they stay aligned because of the strong interactions between the atoms that make up the system. So I'll tell you more about the magnetic potential energy, well, next week, I guess, right? We have a date this Wednesday. Okay, have a nice day.